Welcome to MathGPT. Today, we're going to learn about electric potential, a fundamental concept in electricity and magnetism. First, let's understand what electric potential actually is. Electric potential at a point is the work done per unit charge in bringing a small positive test charge from infinity to that point against the electric field. Its SI unit is the volt, symbolized by V, where 1 volt equals 1 joule per coulomb. Now, let's look at the formal definition and formula for electric potential. By definition, the electric potential V is equal to the work done W in moving a test charge from infinity to position, R, divided by the value of the test charge Q test. For a point charge Q, the potential at a distance r from it is given by V of R equals K times Q divided by R, where K is Coulomb's constant, approximately 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Note that we're choosing the potential at infinity to be zero, which is a common convention in electrostatics. The superposition principle is very important in electrostatics. If multiple charges Q sub I are present, the total potential at any point is simply the algebraic sum of the potentials due to each individual charge. So, V total at position R equals the sum of K times Q sub I divided by R sub I, where sub I is the distance from charge Q sub I to the point of interest. Let's visualize this with 2-point charges. The total potential at point P is the sum of the individual potentials due to each charge. Now, let's explore the important relationship between electric potential and electric field. The electric field, E, and potential V are related through the gradient operator. The electric field is equal to the negative gradient of the potential. In one dimension along x, this simplifies to E sub x equals negative dV by dx. This means that the electric field points in the direction of decreasing potential. Let's visualize this relationship. The electric field is perpendicular to the equipotential surfaces and points from high potential to low potential. Let's now discuss electric potential energy, which is closely related to electric potential. A charge Q placed at a point of potential V has potential energy U equal to Q times V. When a charge moves from point A to point B, the change in potential energy is given by delta U equals Q times the quantity V of B minus V of A. Let's visualize this with an example. When a positive charge moves from a high potential region to a low potential region, it loses potential energy. Conversely, moving a positive charge from a low potential to a high potential requires external work to be done. Let's work through an example to solidify our understanding. Suppose we have two like charges Q1 and Q2 fixed in place. What is the electric potential at point P, which is 2 meters from Q1 and 3 meters from Q2? Using the superposition principle, the potential at point P is V sub P equals K times Q1 divided by 2 meters plus K times Q2 divided by 3 meters. Let's calculate this with specific values. Suppose Q1 is 2 microcoulombs and Q2 is 3 microcoulombs. Plugging these values into our formula and calculating, we get V sub P equals 9 times 10 to the power of 9 times 2 times 10 to the power of negative 6 divided by 2 plus 3 times 10 to the power of negative 6 divided by 3, which equals 9 times 10 to the power of 9 times 1 times 10 to the power of negative 6 plus 1 times 10 to the power of negative 6, which equals 1.8 times 10 to the power of 4 volts. Let's summarize some key points to remember about electric potential. First, potential is a scalar quantity. It has magnitude but no direction. Second, the zero of potential is arbitrary. It's often chosen to be at infinity. Third, equal potentials form equipotential surfaces, which are always perpendicular to electric field lines. Finally, moving along an equipotential surface does no work on a charge since the potential doesn't change. Let's try a quick practice question to test your understanding. A charge of positive 5 microcoulombs sits at the origin. Part A. What is the potential at R equals 0.50 meters? Using the formula V equals K times Q divided by R, V equals 9 times 10 to the power of 9 times 5 times 10 to the power of negative 6 divided by 0.5, which equals 9 times 10 to the power of 4 volts. Part B. How much work is done in bringing a positive 2 microcoulomb test charge from infinity to that point? Using W equals Q times V, W equals 2 times 10 to the power of negative 6 coulombs times 9 times 10 to the power of 4 volts, which equals 0.18 joules. To conclude, Electric potential is a fundamental concept in electrostatics that helps us understand how charges interact with electric fields. Remember that the potential at a point tells us the work done per unit charge in bringing a test charge from infinity to that point. It's a scalar quantity, and it's related to the electric field through the gradient relation. The principles we've learned today apply to countless real-world applications, from batteries and capacitors to medical devices and particle accelerators. Thank you for watching this introduction to electric potential. I hope you found it helpful and insightful.